Hello everyone, this is Ms. Herman and I'm doing the calculations out of the physics assignment 1C. We did a bunch of these, so we did problems 1 and 2 on Wednesday, we did part of problem 3 on Wednesday, we did the rest of problem 3 today, we also did at least 4A today. I'm going to redo 4A and do 4B, I think we set it up. And then I'm going to do the bonus problem, C. Some of you might be watching this thinking, I just want to skip ahead to C. Like, I don't want to see, I don't need all that other stuff. Once I do this video and post it, I will find the timestamp for when that begins, and then I will let you know what that is. All right. So we have an egg that we dropped from the ceiling, figuratively, dropped from the ceiling in the classroom. We figured out how long it takes in the classroom. We figured out how fast it is when it hits the ground in the classroom. Then we said, all right, well, why don't we drop it off the Space Needle? So that's a lot taller. So we found out that it takes a lot longer to get there. I think it was less than 1 second in the classroom. But then here from the Space Needle, it takes about 6 seconds. When we took a look at how fast it was going from the Space Needle, we were a little shocked because 60 meters a second comes out to about 100 miles an hour. It's pretty fast. All right, so now we're saying, all right, we're going to go to Mars. I mean, we've been doing all this math on Earth. What if we went to Mars? So there we're going to build a tower as high as the Space Needle. So we're going to have that Space Needle again. And we're going to actually time how long it falls. So we go there with a really accurate stopwatch, and we determine it takes 9.95 seconds for the egg to fall. Great. So here we're going to find out some things. So we want to find out what's the acceleration of the egg on Mars. Here on Earth, we know what the acceleration is, but once we change planets, the acceleration changes. On Mars, Mars is less massive than the Earth. So it pulls on it less, so the force of gravity is a little bit less, so the acceleration is also a little bit less. We're going to find that what that is. Then, oh look, there's that question again. How fast is the egg going when it hits the ground? So we've done that twice now. We should know how to do that. Then we have this one, which is how tall would your tower on Mars need to be for the egg to hit the ground with the same velocity as when the egg hit the ground from the Space Needle on Earth? Oh, that's a big question. We're going to save that. All right, let's do 4A first. I'm going to go through the same process that we went through in class. So that is, what do I know? What do I want to know? And then how am I going to get to what I want from what I have? So here are some things that we know. We know the distance, right? Because we're building the Space Needle again. So we know how high the Space Needle is going to be. We know the time because it told us that it takes 9.95 seconds. I'm going to label this 4A so we know what's happening. What do I want to know? I want to know the acceleration. All right, so how can I get that? We have a couple equations we've been using. We have the distance formula equation relating distance, acceleration, and time. We also have this acceleration equation that takes velocity and time. In this case, I have the distance. I have time. This has this extra thing here for initial velocity. But just like before, my initial velocity is 0. So I know what that is because the egg isn't moving. All right, so let's use this equation. D equals 1/2 AT squared plus the initial velocity times time. In this case, the initial velocity is 0, so I can ignore this because that's equal to 0. So let's put in some numbers. 184 meters equals 1/2 times A times however long it took, which was 9.95 seconds, squared. Don't forget the squared. Here's my great calculator, also known as my, oh my god, you just saw the code to my phone. You could break in and do stuff. Okay. What's my number? 9.95 times 9.95 gives me 99.0025 times A times 1/2 equals 184. So I think to get A, I'm going to take 184, I'm going to multiply it by 2, and then divide by 99.0025. All right, so that gives me 184 times 2 divided by 99.0025. All right, 3.7171. That goes on for a while. So we're going to round this. This was 3 digits. This was 3 digits. So I'm going to round it to 3.72. What are my units on acceleration? Meters per second squared. Just for fun, 184 is meters. 2, just a number with no units. Oh, I'm a little off the page there, sorry. This was second squared, right? Because I had seconds and then I squared it. Second squared. So look, there's the units I want. Meters per second squared. Nice. Let's take a look at, that's too reflective over there. Still on the screen. All right, let's take a look at 4B. Okay, how fast is the egg going when it hits the ground? All right, so I know all the same things I knew before. I know distance and time. But now I also know acceleration, because I just figured that out. Acceleration. What I want to know is velocity. And how do I get there? I've said this casually, but I want to say it kind of seriously now. If I take a look at my equations, take a look at this equation. Notice that it has distance, so it has d. It has a for acceleration. It has time in it, and it has velocity. So take a look. I have distance, time, acceleration. Velocity is what I want. Why can't I use this equation? Well, the reason is because this velocity is VI. It's the initial velocity. And what I actually want is something called VF, or the final velocity. If I look at the other equation I have, this delta V is the change in velocity. So technically, it's not what I want either, because the change in velocity is not the same as the final velocity, except it is in this case, because I started at 0. So since I started at 0, the final velocity is going to be how much it changed from 0 to the change. We're going to do some problems in the future where my initial velocity isn't 0. So that's why I keep writing it and then crossing it out when my initial velocity is 0. So in this case, the change velocity is equal to the final velocity because I started at 0. And then however much it changes is how much I'm going at the end. Great. I'm going to use my friendly circle. Friendly circle. All right, so I want velocity. That tells me, I'm going to cover that up. That tells me I want A times delta T. All right, so my change in velocity, which is equal to the final velocity, is equal to acceleration times how much time passed. So this is my acceleration, 3.72 meters per second squared, times my time. Where was my time? Wait. Oh, up here. I forgot. I hadn't calculated it. It was in the problem. 9.95 seconds. So now I get to take that number, look, it's still on my calculator, and multiply by 9.95. So this came out to 36.985 units. Well, velocity is meters per second. Let's just do a fun little thing where I check the units times, oh, look at that. So I have meters over second squared times second. That'll cancel out and leave me with just one S, meters per second. Nice. How many digits should I round this to? Well, this is 3 digits. This is 3 digits. So I should round it to 3 digits. Watch how tricky this is going to be. 36.9, so I should round it, which means I should round this up, but it's already at 9, which means I'm going to round it. Okay, so this actually becomes 37.0. And this 0 lets me know that I have, that I measured it to this place. Like, it's not just 37. It's 37 and no tenths. Like, it's really close to 37 meters per second. All right, well, how does that compare with how fast it was going from the Space Needle? So if I look here, I see when I did it on the Space Needle on Earth, it was 60 meters per second. And then when I did it here, when I did it on Mars, it was only 37 meters per second. It's going slower because, that's right, the Mars is less mass, and so it pulls less gravity. Okay, I can just see that I'm right now at 1025. All right, I can put that in the notes. All right, so now let's go with this really hard problem. And for the really hard problem, I'm going to use this big space of white space over here. Okay, so here's the question. Where can I put this? I guess I'll put it off the screen. I didn't really want to because I kind of want it. Okay. Okay. So here's our situation. It's always nice to draw a picture. There's the Space Needle. I know that when my egg starts here at the top, I know that its initial velocity is 0. And then when it hits the ground, I want the final velocity to be whatever it was when it was on Earth. So here it is, 60 meters per second. All right, so I want it to be 60 meters per second. Okay. What else do I know? So I know the initial velocity. I know the final velocity. I know that acceleration due to gravity on Mars. Yes, physics loves to have little subscripts. So I know the acceleration on Mars. We got that as 3.72 meters per second. So these are all the things I know. This is what I know. All right, what I want to know is what's this distance? Right? So how high do I need to build this in order to get this speed? Conceivably, it needs to be higher, right? The longer it falls, the faster and faster and faster it goes. All right, so now how can I get there? How can I get there? Let's take a look. I have some equations. I have this equation, d equals 1/2 at squared plus initial velocity times time. So I have this equation. And I have this equation, acceleration equals change in velocity over change in time. All right, so what of these things do I know? Oh, a highlighter would be great here. Let's do that. Okay, so I know acceleration. And do I know the change in velocity? I do. I know initial velocity is 0. I know the change in velocity is 60 meters per second. It goes from 0 to 60, so I know that. But what do I want to know? I want to know d. I could find out d if only I knew what the time was. So how can I find out the time? Well, if I look at this equation, there's where I can find out the time. So this equation, I have 2 things I know and 1 thing I don't. So if I use this equation to find out the time, then once I know what t is, I can put that in for how much time has gone by, and then I'll be able to find d. So this is a multi-step problem. That's why it's a bonus problem. All right, let's give it a try. We're going to start here. What I want is time, friendly circle. A is change in velocity over change in time. So I want this. Cover that up. So to find my change in time, I'm going to do the change in velocity over acceleration. All right. Change in time. My change in velocity is, I'm going from 0 to 60, so my change is 60 meters per second. My acceleration on Mars is 3.72 meters per second squared. Oh my gosh, those units are really freaking me out. I know, just wait till next week. All right, so what I have is my change in time is 60 divided by 3.72 equals, oh, there's my phone again. All right. Oops. All right, so I have 60 divided by 3.72 equals 16.129 seconds. Or the time elapsed by the time it hits the ground is this. I have 2 digits, so I'll round it to 2 digits. 16 seconds. That's a long time. Remember we were thinking about how 6 seconds was a long time? 16 seconds is even longer. But again, remember, for it to get up to speed, it needs to accelerate for a longer amount of time. All right, so I have T. Oh, I'm going to highlight it that I know it, but I'm going to do it in a different color because I just figured it out. All right. Well, it looks the same color to me on the screen. Great, Miss Herman. All right. So now I'm ready to find D because now I know the elapsed time. So D equals 1/2 AT squared plus the initial velocity times time. Initial velocity, 0. Yes. All right, my distance, let me make a little mark here. My distance equals 1/2 times the acceleration, there it is, 3.72 meters per second squared, times seconds, 16 seconds squared. So that means I have D equals 1/2 times 3.72 times 16 squared, 256. All right. So now I get to multiply. So 256 times 3.72 equals divided by 2. Oh, not what I wanted. Go away. Of course you're getting hot. We're like really doing some thinking here. Ugh, now I got to do it. Okay. 16 times 16 equals 256. 256 times 3.72 equals divided by 2 equals 476.16 meters. How many digits? I'm going to leave 3. Meters. So that's how tall it needs to be. So yeah, on Mars, it's pulling a lot less. I need it bigger so it has time to speed up. Oh, a fun little check on units. Let's check on, I didn't do checking on units here. So I have meters per second here being divided by meters per second squared. I'm going to rewrite that as meters per second divided by meters per second squared. Oh, put that on the screen, Miss Herman. Okay. Then the rule is I multiply by the opposite. So instead of dividing by division, I multiply by the opposite. Multiply by s squared over m. Cancel, cancel. This seconds takes out one of those s's, and I'm left with just seconds. So that's how the units come out on that one. Let's take a look at this one. This one, my units are meters per second squared times seconds squared, which means I end up with meters per second squared times seconds squared, and these cancel out, and I end up with meters. All right, so let's get to Mars so we can build a Mars needle, because we're in Mars and not just at space, and we'll build it this high. Thanks for watching.